We had one little scheduling change. It has been updated on the website. So Anand Sarwate, who was going to be the second talk in the afternoon, wasn't feeling well. So we swapped him with Aaron Wagner, who is in a different room working on his talk. So that'll be the second talk after Haewon. So our first speaker is Haewon Jeong from UCSB, who's going to be talking about fairness without imputation. Take it away.
Thank you, Oliver. Thanks everyone for not missing my talk about missing values. I know it's hard to stay focused after lunch, so I try to keep it lighthearted as much as I can. So we live in an interesting time, and maybe that's an understatement. We live in a freaking exciting time. How many of you have watched the South Park episode on ChatGPT? Which is also written by ChatGPT. Oh, not many of you. Well, to be honest, it's not one of the funniest episodes they have, but I think it's still worth it to watch it because it's like monumental, because you know you really made it when you have a whole South Park episode dedicated to you, right? And how many of you have students who submit their homework listing ChatGPT as a collaborator? Okay, I see one hand.
Should list it.
Exactly. At this point, you should question your students' honesty. So like this was the actual homework in my class. It was like homework 1. It was like a math review kind of homework. So I asked them to type their answers in LaTeX. And this very honest student told me that she's not familiar with LaTeX. So she used ChatGPT to get help with the LaTeX part. And she submitted the perfect homework. She's a great student. She's actually now working with me on very interesting problem related to generative AI. So we live in this time where these exciting AI technologies are coming out. That's going to change permanently how we work or how we create. And I think we are all gathered here today because we are kind of people who thought about different kinds of failure modes of these AI technologies. I mean, these technologies are awesome, like mind-blowingly awesome, but they're still not perfect. They still have different kinds of failure modes. And we've been thinking about whether they can fail to protect people's privacy or whether they fail to perform safely and robustly in different kinds of environments and so on. And one of such failure modes, which is now well known in the community, is unfair performance of predictive models. So when we trained a machine learning model algorithm for criminal justice, it was biased against Black criminals. And when we used a machine learning based ad recommendation algorithm, it was showing different ads for different genders and different races. And there were many facial recognition algorithms that work really well on white guys, but not as well on other demographic groups. And in this talk, I want to introduce you to a different kind of failure mode maybe you haven't thought as much about, which is unfair performance in data pre-processing, especially pre-processing missing values. So missing values are simply missing entries in your data set. And in real world data sets, they're really everywhere. For instance, in survey data, there can be a lot of missing entries because people don't answer all of the questions because they don't feel comfortable answering all of the questions, or they're just feeling lazy to answer all of the questions. And electronic health records notoriously have a lot of missing values because each row of the table is a record of one person. And not every individual takes the same set of medical tests. So if an individual doesn't take certain medical tests, those entries are left empty. And also in police reports, when police officers are filing for crime reports, they don't fill in all of the details. So a lot of entries are left empty. And one interesting observation I made when I was working with this high school longitudinal study data set is that this data missing pattern is not independent of sensitive group attribute like race or gender. So I'm just showing 3 example variables here. And then I'm showing missing rates for different races. So I'm showing missing rates for white and Asian students and missing rates for Black, Hispanic, and Native American students. So you can see that for all of these variables, missing rate is substantially higher in Black, Hispanic, and Native American students. And for some variables, like secondary caregivers' highest education, it's as high as, the difference is as high as 15%. And then we train a machine learning model on the training data that have this kind of disparate missing patterns. And then we use those machine learning models to make decisions on individuals that can have like significant impact on people, such as we can make education related decisions, whether to give an admission to this person or not, or we can make very important medical decisions or like bail decisions in criminal justice. So now the question I'm asking is, then can we still train a fair model after pre-processing these disparate missing patterns that exist across different demographic groups? Is this question clear? Okay, so when I pose this question, I think the first question I get is, how do you even define fair or fairness? And I assume like this audience is pretty familiar with fairness metrics, but I'm gonna just give you a brief review. So I am gonna consider group fairness metrics. And for this, we are looking at performance metrics per groups. And in this case, I'm gonna consider binary groups for simplicity. So S equals 0 is a minority group and S equals 1 is majority group. And then again, for simplicity, we're gonna assume that we are giving out binary prediction y hat. And then the basic concept of group fairness metrics is that performance metrics of machine learning models should not depend on this kind of sensitive group attribute. So depending on how we measure the performance of machine learning model, there are different types of group fairness metrics. When we care about equalizing positive rate, which is probability of y hat being 1, then that group fairness metric is statistical parity. And when we want false negative rate between two groups to be equal, then that group fairness metric is equalized opportunity. And when we want to have equal accuracy across two groups, that's accuracy parity. And in the ideal world, we want the gaps in these metrics to be exactly 0, but that's not always possible. So what we do is we take the group-wise difference for these metrics, and we want to make the difference as small as possible. So as I mentioned, this unfairness in predictive models that has been studied a lot in the literature. So people have looked at how to design more fair algorithms when we train a predictive model here. So we basically what we are trying to do is we want to reduce these differences when we are training a model. So then the problem is when researchers develop or evaluate these new fair models, they usually use clean and curated data that don't contain any missing values. However, in real world, most data sets are not as clean. They have a lot of missing entries and we have to do a lot of data cleaning. So there's a long data pre-processing step that comes before actually training a model. And people even say that data scientists' time is spent 90% on data cleaning, not actually training a model. So the question is then, what about fairness issues that could arise here? A lot of people say that, oh, machine learning models are biased because the data is biased. But then if we are not careful about our data pre-processing steps, can we actually introduce more bias in the data that will harm the predictive model we're going to train later? And especially what we care about is pre-processing missing values. So let's see what exactly happens in the data pre-processing step. So when there are missing values, you can either drop entries that have missing values, or you can do something called data imputation. And usually data imputation is a much better way for a better performance when you have sufficient number of missing entries. So data imputation is basically filling in missing entry with a new value. It could be mean imputation. You take the mean of the column and impute that value. Or it could be median imputation, or you can do something more sophisticated like KNN imputation or multiple imputation and so on. And looking at learning with missing values, dealing with missing values, it's a classical problem. People have looked at this problem for decades. And learning fair models that have been a very active area of research in the past 5-10 years. However, these together, fairness in imputation, that hasn't gained a lot of attention from the community. In fact, when we thought about this problem, we only found 2 previous work, Fernando et al. And Wang and Singh et al. And they mostly did empirical study on how different imputation methods can affect fairness metrics they care about. But we wanted to, and there are some more work that came after our work or around the same time. And our work asked somewhat more fundamental question. And the question we're asking is it sufficient to do data imputation first, and then apply a fair learning algorithm on the imputed data? So let me elaborate a little bit more on this. So if we take all the steps that come before data training as a black box, and then we take state-of-the-art fair learning algorithm here, and then train a fair model here, is it sufficient to guarantee good fairness in the final model?
What does the fair learning model mean? Because my learning model is actually applied to that data set and it's learned on that data set and it's matched to that data set. So, I mean, the data set cannot be a black box the way you put it. Or I mean, sure, you can have data processing, that could be a black box. But if you pick a fair metric that has to be for this data set, unless we're just, and so you design a fair algorithm, it's for this data set, right?
Okay, I think that's a fair point. So you will design a fair learning algorithm or take a fair learning algorithm that works well for this particular data set. And then you have only a view of this data set after it got pre-processed. So I think you're right that it's not, data set itself is not black box, but then the steps that come before this data set is a black box. Yeah.
But we're not talking about the data set, we're talking about the distribution, right? So the data set is reflects the distribution, but it's not equal to 1. Right?
Right.
When you define fairness, it's defined in respect to the underlying distribution, not the underlying data set.
Yes, but one way or the other, you make that assumption from so you learn that. Unless you're making some assumptions on the distribution.
Sure, but the fundamentally the fairness metric is it's a function of the model and the distribution. The data set is just a means to the end.
That's correct.
Ideally, yes. Sorry, keep going.
Okay, any other questions? Thanks for the question. Okay, so I think the question is clear now. So towards answering this question, we first did a theoretical analysis that analyzes different risks of this disjoint process of data imputation and model training. And each theorem shows different kinds of risks. And I'm going to go more into details of each theorem soon. But let me just highlight the last theorem. So last theorem is an impossibility result that shows that there is no universally fair imputation method for different downstream learning tasks. So if we want to learn different models, such as logistic regression or a neural network, then one imputation method might not be sufficient to perform well for both of those models. So this kind of inspires us to develop a more integrated approach between imputation and learning. So that's our second part of contribution. So we propose this algorithm called Fair MIP Forest, which integrates this processing of missing values and fair learning into one algorithm. And then we show through experiments that this approach, Fair MIP Forest approach, achieves better fairness accuracy trade-off. If you don't understand this graph, don't worry about it. I'll get back to it later. So let's go a little bit more into our theoretical analysis. So the first risk is showing that the performance of imputation method itself can be biased. So we have data set with missing values, x tilde, and then we do the imputation and fill those in. And then in this part, we quantify the performance of imputation method using L2 norm. So if this data set has missing entries, we compare the imputed value and the original data, and then get the expected L2 loss. And then what we care about is the group-wise difference in this imputation performance. And what we show is the following. So let me break this theorem down a little bit. So we first make simplifying assumptions that data are missing completely at random, which is a common assumption that is made in the learning with missing values literature. And then we also make another simplifying assumption that the set of observed variables is an empty set. And then we show that the imputation performance gap between group 0 and group 1 is upper bounded by this term, which consists of missing rate difference between two groups and mean difference between two groups and variance difference between two groups. So if group 0 and group 1 have identical distribution, then there won't be any gap in imputation performance, but that's usually not the case. And when there is some difference in the data distribution for group 1 and group 0, and also a missing rate difference, and this is the upper bound of the imputation performance gap it could have. And then the second theorem shows the risk of mismatched imputation methods. So let me explain a little bit more about what that means. So let's say an entity trains a model on the data that have a lot of missing values. So they have to use some kind of data imputation technique when they're training the model. But when they're releasing their trained model to their clients, let's say, then they might not be able to disclose their imputation method in all details. Maybe they were just lazy about it and they didn't disclose all the details, or in some cases, they're just not able because disclosing all of this imputation algorithm could actually leak some, privacy. Let's say they use mean imputation, and giving out a lot of mean information can violate differential privacy. So when a client gets this trained model and applies this model on their testing data, they might have to choose their own imputation method, which might not exactly match the imputation method that was used during the training time. So when there's this mismatch between training time imputation method and testing time imputation method, now we are measuring, again, group-wise loss for group S. And then we apply imputation first, and then we apply this trend classifier, and we want to quantify the gap between two groups of this metric. And then what we show is that, again, we show an upper bound that testing time performance is upper bounded by training time performance gap plus this term, which is distribution shift caused by mismatch imputation, which is measured with total variation distance. But again, this is upper bound. We're not saying that whenever there's a mismatch imputation methods, we are going to have a larger bias. What we are saying is that because of the mismatched imputation methods, the fairness constraint we impose during training time may not guarantee fairness during testing time. So we have to have that in our mind. Okay, and the last theorem is saying that imputation without being aware of the downstream task is somehow fundamentally suboptimal. So to state this theorem, let me just introduce a few more notations. So a lot of fairness intervention methods can be thought of as constraint optimization problem. So we are doing a user optimization here, but then we have this constraint. So we have this different loss function, little l, and we want to make sure that this loss function is similar between group 0 and group 1. So it's bounded by small number epsilon. And when we use imputed data, everything goes through the same, but we are first doing imputation and then applying this classifier H, and then we want to make sure that everything works the same way, even with this additional process of imputation. And then the question here is there a universally good imputation method fimp that can guarantee fairness, which is given by this constraint, and accuracy, which is given by this loss function for any model class H? And then, so again, to show it with more graphics, is there any good imputation method here that could have, good fairness and good accuracy for two different kinds of machine learning models? And we show that that is not possible. We show a simple counterexample that's showing that this is not possible. So inspired by these risks of disjoint process of data imputation and training, we proposed a fair MIP forest algorithm. And let me tell you a little bit more about how fair MIP forest algorithm works. Okay, so this fair MIP forest algorithm combines two existing ideas. First one is missing an attribute. And then the second idea is fair decision trees. So decision trees have a very natural way of dealing with missing values. So we don't always have to do data imputation before training a decision tree. And that is by using this idea of missing an attribute. So instead of filling in all of the missing entries, we can leave those missing entries as they are. And then when we are splitting at each node, let's say we're splitting on feature 2 at this node, then we just have one more check whether feature 2 is missing or not. So in this case, when feature 2 is missing, we are sending all of those entries to the left. And then for those entries that are not missing, that we are doing the regular decision tree splitting with a threshold 1.5. And we do something similar here at this node. When feature 0 is not missing, it goes, now it's following this threshold, and when feature 0 is missing, it's going to go to the right, and so on. So that now we don't have to do imputation using this idea of missing an attribute. So that problem is solved. And then the next question is, then how do we impose a fairness constraint we care about, such as statistical parity or equalized odds? So for that, we use this idea of fair decision tree proposed by Agay et al. In 2019. So they formulate training a decision tree as a mixed integer program. And formulating decision tree training as a mixed integer program is not a new idea. It's been done before, but they add this fairness constraint to the objective function. And the reason why we want this mixed integer program is because the usual way of training a decision tree is a greedy algorithm, where at each node we are maximizing or minimizing some kind of objective, but then we can't really guarantee that we are minimizing a very explicit loss function. So to have this explicit loss function with the fairness regularizer, we're going to use integer programming approach. So there's a lot of notations here, but you don't really have to worry about any of this. So really what you have to know is the objective function, there's explicit loss function, which consists of the regular loss part and then fairness regularizer part. And this fairness regularizer part can represent all the fairness metrics I mentioned, like statistical parity, equalized odds, and accuracy parity. And then we have these variables. These are binary variables. So now splitting at each node in a decision tree just becomes binary variables in this integer program. But when they formulated this fair decision tree algorithm, they didn't really think about missing values in the training data. So we add this additional variable m, which denotes the data missingness. And then we incorporate this idea into the MIP formulation, and everything worked out. But one concern you might have now is that integer program is very computationally expensive. Does it make sense to do integer programming? So it takes hours to just train small decision tree using integer program. So what we did is we just train each tree with a given set amount of time, let's say 30 seconds or 1 minute. But then we take an ensemble of those trees, and we observed that just having an ensemble of these trees, like let's say 20 trees, perform so much better than one tree that was like optimized for hours. So that's where the forest part comes in. All right, so now we have this algorithm. So we wanted to do some numerical benchmarking of this algorithm. So the goal is to compare the disjoint process of doing imputation first, and then applying a fair learning algorithm. and our proposed fair MIP forest. And to do this, we use two very commonly used dataset, Compass and Adult, and high school longitudinal study dataset, which really motivated this project. And then for the fair learning algorithm, we have three different benchmarks: disparate mistreatment, reductions approach, and equalize all the post-processing. And for imputation method, we tried mean imputation and KNN imputation. And let's look at the result. So for Compass, for both Compass and high school longitudinal study dataset, y-axis is accuracy, and x-axis is group-wise difference in false negative rate. So we want this difference to be as small as possible. So being on the left side on the x-axis is a good thing, and we want accuracy to be as high as possible. So what we want is the highest curve as possible, which shows the best fairness accuracy trade-off. And then these circles are mean imputation, and these squares are KNN imputation. And for all different kinds of combinations of mean imputation, KNN imputation, and different fair learning methods, we can see that this integrated approach using fair MIP forest has the best fairness accuracy trade-off. Okay, so I think I have enough time. So again, as I mentioned in the beginning, this problem of looking at fairness in missing values or fairness in data pre-processing, I think is a largely unexplored area. For instance, what we did in this work is integrating imputation methods into the learning algorithm and making it as like a one process. But in some cases, you will have to do data imputation. Let's say you are like the entity who's collecting the data, and when you're releasing your data, you might have to do data imputation and release the complete data for your client. So there are situations where doing imputation is unavoidable. Then can we at least make sure that this imputation method has some kind of fairness guarantee? And can we design a fair imputation method? I think this is really largely an open question. And then in this work, we really focused on using decision trees and this nice property of missing an attribute to integrate imputation into learning. But can we do the same thing for other machine learning models like neural networks? And I think our co-authors, Flavio and Hao, have been working on this problem and been extending this to other classes of models like linear models. And I think this problem is somewhat fundamentally information-theoretic problem, because missing values is basically going through these erasure channels. And we've been thinking about having these erasures and reconstructing it using error correcting codes for a long time. And can we borrow those information-theoretic insights to solve this problem? So I think that's an exciting direction. But missing values is, again, not the only step in data pre-processing stage. There are many other steps like data balancing and data encoding. Let's say you have a mix of real valued entries and like text entries, then you would have to somehow convert the text entries into real valued number using maybe text embedding techniques and so on. And could they actually bring in more biases in the data when it comes to the model training stage? And I have some undergraduate students at UCSB working on this question. And I think there's a lot of interesting questions we can address here. And thanks for your attention.
Plenty of time for questions.
Ask another question. Yeah. Can you go back to your tree, forest tree thing? So implicitly, a tree is building the empirical statistics of the data to learn a tree, right? So by allowing for this missing, you're sort of explicitly taking care of the statistics of the missing data in some sense, right? So is that how you get, and then explicitly writing that out into your fairness requirements? Is that the key intuition in getting these getting it? So if you go back to that AP longitudinal data, do you see, does something change? I mean, I know you showed us some results, but I'm trying to make a connection from here to like, what does it mean to be fair when there's missing data? Like, you don't really know that data point, but are you?
Yeah, so I think you're absolutely correct that so by training this tree, we're basically we're not doing imputation, but somehow we are doing implicit imputation. Because by saying, oh, missing values are going that way or that way, so we are doing some kind of imputation, but this is not imputing just one value. You can think of it as doing assigning a range of values. And then your next.
So the question is, so this is just say demographic parity or statistical parity. How does this help? Get statistical, that part is not entirely clear.
Okay, so I think one way to think about this is when you do imputation, and then you optimize something for imputation, and then you apply fair learning algorithm, which you can think of it as like constraint optimization algorithm, right? And then now we are kind of thinking about this whole thing as one constraint optimization problem. So it's always better to have this one constraint optimization problem than having like two, optimization problems separately.
Okay. Yeah, last it off.
Yes.
You also assume that the data are missing randomly, or what is the?
So for proving theorems, for most part, we're making this MCAR assumption, which is missing completely at random. But for experiments, we're not making any assumptions like that. So for high school longitudinal study data set, we're not making any artificial missing values. But data set itself already has missing values, and we're just processing that missing values.
But if they're missing at random, but there is a correlation with sensitive groups, right? Like for some sensitive groups, it's more missing.
Yeah, so that's a good point. So it's missing completely at random per group. Yeah. So for the theoretical analysis, that's what we assume. And then for experiments, we're not assuming anything.
So maybe related to the assumption, can you go back to your slide where you had the theorem? So there was a second assumption, and I'm afraid I missed what it meant. You said the set of function data is empty.
Oh, yes.
Can you explain what you meant? I think I missed it.
Yeah, so that's a great question. So again, like in this case, like we're kind of showing really simple counterexample type thing. And then here, so what this means is that let's say you have a data point of 2 dimensions. Then when the data is missing, then both entries are missing. So it's either you observe both of them or nothing.
I see. You erase the entry.
Yeah, basically, yeah.
So the entire row is gone? Is that what that means?
Entire row is gone except the sensitive attribute. Yeah. So it makes sense if you think about, I think, mean imputation. So when we get the best imputation method here for minimizing L2 norm, imputation method will be the best one, will be mean imputation. And then when you take the mean, then because the distributions are different now you have gaps in performance. Yes.
If I understand theorem 3 correctly, it says for any imputation method, there exists H1, H2 model classes for which if you achieve accuracy and fairness for H1, you cannot achieve both accuracy and fairness for H2. Is that correct?
So we can say that for any like H1 and H2, if this imputation method performs well on H1, it won't perform on H2. I think what we are saying is there exists H1 and H2.
And is it that these H1, H2 are reasonable, or like, can we say that exists? Because for example, if H1, H2 are singletons, maybe that's not very practical. Like in practical situations, H1 and H2 are rich enough. Can we say that there exists rich enough H1 and H2 to which this also happens?
I don't think we have thought about rich enough H1 and H2. And again, when we are proving this theorem, we use very simple counterexample. I think H1 was just using one feature for classification, and H2 is like using the second feature for classification, and then showing that one imputation method cannot work well for H1 and H2. But I think that's a great question.
Great, thank you very much. Next up is Aaron Wagner from Cornell, who's very graciously